Now, to solve it optimally, if we think of what data structure we can use so that for every window, we can maintain the maximum, we can find the maximum efficiently. So, what data structure comes to our mind when we think of that we have to find the maximum efficiently? In such cases, of course, we know that maximum priority queue can help us. So if we go with the idea of maximum priority queue, we are aware that it provides us a function. We can insert an element. Let me call that function to be add, and this works in log n time. Then we can get maximum element. This works in constant time. And then we can remove minimum element. This works in log n time. Now, if you think of, we do not have ideally remove x function. And even if MaxPQ supports remove function, it will work in n time complexity. So being aware of function of MaxPQ, let's see if we can apply this to solve the problem efficiently. Now for first window, what we can do is we can take a MaxPQ. First window has 9, -6, 8, and 4. So what we can do is we can put all of them into the MaxPQ. 9, -6, 4, and 8. Now, if we have put all these elements or W elements into MaxPQ, let's say roughly time complexity will be W log W, because every element inserts in log W time complexity, and we are inserting W elements. So this is for first window. Now getting the answer will be very efficient. We can get the maximum line. Now when we shift the window, for every shifting of the window, now 3 is coming in. So we put 3 over here. And 9 is outgoing, so we have to kick out 9. That means if we have to kick out 9, we'll have to use remove x functions, because it is not necessary that every time outgoing element is max element, right? So we will have to remove x. So this is going, this is coming. Now same way, again we shift the window. This time if you notice, outgoing is -6, and -6 is not max. So when we are removing -6, again the time complexity is going to be kind of max priority will have at max W elements. So for remaining windows, we totally have n minus W windows remaining. And when we are moving, the time complexity is incoming element we are adding. So addition of element will be log W, but outgoing element is going to be time complexity of W. Yeah, because of removal time complexity. So this makes our solution to be big O wise. If you look at big O wise, we have n into W solution, because this is W log W, but here we will get n into W to be the major factor. This is a significant term that we will have. So if W happens to be n by 2 in input, this is going to be kind of n squared time complexity. So this solution isn't going to give us the efficient outcome, the efficient solution. Yeah. Now, there exists a way to continue using MaxPQ and still solve the problem efficiently. Let's see how. What we will do is we will use a notion called lazy deletion. So what it means is we'll not remove the element unless it is very necessary. So delay deletion of element. Okay, and second thing what we will do is we will store element and index pair in MaxPQ. Now when the first element comes 9, let's put 90 into the MaxPQ. Second element is -6, let's put -61 into the MaxPQ. Then comes 8, 2, and then comes 4, 3. Now the current window we are looking at, our current windows start and end, if I keep track of, my start index is 0 and end index is 3. So this is where my current window is. Okay, now if we have to find the max, we will select the max based on the highest value, not the index, but the value. Okay, so this we got. Now, when we shift the window, when the window shifts, we'll not worry about removing 9. 9 will stay there in Maxi by MaxPQ. So window is shifting, we enter window 1, 4. And what I said is, we'll bring in the element, but we'll not remove the element that is already there. Yeah. So shift the window, avoid deleting, but include the next element. Okay, so now we have 5 elements in our MaxPQ. Now, if we ask what is the max element will turn out to be 9. But we stored its index is 0, and current window is telling us 0 is outside your window because it is less than S. So at the time of getting the max element, we know that this cannot be the max because this has gone out. This time we delete it. So basically what we are saying is we are delete on get max for a window. Okay, so now 9 cannot be the max. So we continue to delete as long as the max element we are getting is outside the window. So we again ask for what is the max. This time max will turn out to be 8 2, and 8 is the max. So first window's max was 9 earlier. Now 8 is the max. And 8 is well within the window, so we don't remove it. Okay, let's shift the window again. When we shift the window again, 7 comes in. So 7 5 is inserted. We avoid deleting. Now we ask what is the max. So this time our window shifts from 2 to 5. Now we ask what is the max. The max is going to be 8 2. 8 2 is index 2 is still in the window. So we will print 8 and we will move the window forward. So this becomes 3 and this becomes 6. Now element at index 6 is -1. So -1 comes at index 6. Now we have included the element, but we haven't deleted the element. Now we ask for the max. Max will turn out to be 8, but index of 8 is 2, which is outside our window. So we remove it now. Again, we ask max. Max now turns out to be 7. Its index is 5. 5 is within the range. So this is perfectly okay. We print 7, we move forward. So if we continue like this, that every time we are adding the new element, but avoiding deleting the element. And when we do get max, keep getting the max element. If max element is outside our window, just get rid of it. Yeah, so this would be lazy deletion approach. If we go with this idea, then what would happen? It is possible that our priority queue gets filled fully. Think of it how if array A was 1, 2, 3, 4, 5, 6, 7, 8, 9. So first priority queue would have had these elements. Now when you shift the window, 5 comes in, but we are not removing 1. So now you will have all these elements, but from this window, the max would come out to be 5. So when you shift the window, 6 will come in. In this window, 6 will be the max, but deletion would never happen because none of these elements will turn out to be the max. So in this case, what will happen in worst case till the end, our priority queue size will go up to W. Yeah, that is still okay. Our time complexity of this approach would be first window we have put W log W plus. Now when we are moving forward for remaining N minus W windows, and we are putting the element, let's say no removal happens, so every insertion happens in log n time. Yeah, so overall time complexity of this approach turns out to be now N log N. With extra space of W. Yeah, so this is lazy deletion approach.